A $10 billion telescope was launched into the void with one quiet assumption baked into its design, that we already understood the universe well enough to know what we were looking for. We built it to see further. We did not build it to be wrong. And then the data came back. What the James Webb Space Telescope found in its first 2 years of operation did not confirm our models. It complicated them. In some cases, it directly contradicted them. And the scientists reading those findings, people who had spent entire careers building the theoretical framework that Webb was supposed to validate, began using a word they rarely use in public. Crisis, not anomaly, not discrepancy, crisis. Here's the specific problem. Our best models of how the universe works predict that galaxies grow slowly. They start small, they merge, they accumulate mass over billions of years. That is not a rough sketch. That is a precise, mathematically rigorous prediction that has survived decades of observational testing. Webb looked back to roughly 300 to 700 million years after the Big Bang and found galaxies that had no business being there. Massive, structured, mature, galaxies that looked like they had already lived a full life before the universe was even old enough by our own calculations to have built them. If those observations hold, and so far the more we check, the more they hold, then something in the foundation of modern astrophysics is either incomplete or wrong, not a parameter that needs adjusting. The foundation, that is what this video is about, not the fear of being wrong, but the extraordinary, uncomfortable, genuinely thrilling possibility that a single telescope drifting 1.5 million kilometers from Earth may have just handed us the most important scientific puzzle of the 21st century. Subscribe if you want to follow this to wherever it leads. Now, let's go. To understand why Webb's findings matter so much, you first have to appreciate what we built before Webb arrived, because the standard model of cosmology is not a rough draft. It is one of the most precisely tested intellectual structures in the history of science. The framework is called Lambda-CDM. Lambda for dark energy, CDM for cold dark matter. It describes the entire evolution of the universe from the first fraction of a second after the Big Bang all the way to the present day. And for decades, observation after observation lined up behind it with almost suspicious precision. Here's the basic story it tells. The universe begins unimaginably hot and dense. It expands, it cools. In the first few minutes, protons and neutrons fuse into the lightest atomic nuclei, hydrogen, helium, a trace of lithium. The model predicts the exact ratio of those elements. We measure them across the universe. They match. Then, roughly 380,000 years after the Big Bang, the universe cools enough for electrons to bind to nuclei, and for the first time, light can travel freely. That ancient light is still visible today as the cosmic microwave background, a faint glow of radiation spread across the entire sky. The Planck satellite mapped it with extraordinary resolution. The model predicted its pattern almost perfectly. Then comes the slow, patient work of gravity. Cold, dark matter, invisible, massive, moving slowly, begins to clump. It pulls ordinary matter with it. Gas falls into those clumps, cools, fragments, and ignites as stars. Stars gather into small galaxies. Small galaxies merge into larger ones. Structure builds from the bottom up over billions of years, like a cathedral assembled stone by stone across centuries. That is the picture. And it works. It is not a convenient approximation, and it is a framework that has earned its authority through relentless testing and relentless survival, which is exactly why what Webb found is so difficult to dismiss. This is not a model that was fragile to begin with. This is a model that was supposed to be unbreakable, and that makes every crack Webb revealed worth taking very seriously. Let's talk about what Webb actually found, not the headlines. The data. In early 2023, a team of researchers published findings based on Webb's first deep field observations. They identified a population of galaxies existing between 300 and 700 million years after the Big Bang, a period the standard model treats as a kind of cosmic adolescence, a time when structure was still assembling itself from raw ingredients. What they found in that window were galaxies with stellar masses so high that under the Lambda-CDM framework, they simply should not exist yet. One candidate galaxy, catalogued as JADES GS-Z13-0, appears to have formed within roughly 320 million years of the Big Bang. It already contained billions of stars. stars that, according to our models, had not had nearly enough time to form. Think about that with a concrete comparison. Imagine you are watching a time lapse of a forest growing from bare soil. Your model, built on everything you know about biology, soil chemistry, and rainfall, tells you that a mature oak tree requires at least 80 years to reach full height. And then at the 5-year mark of your time lapse, there it is. A full-grown oak, not a sapling, not an unusually fast-growing tree. A centuries-old oak standing in soil that was bare 5 years ago. That is the category of problem Webb-handed cosmologists. The numbers are not marginal. Some of these early galaxies appear to contain 10 to 100 times more stellar mass than the standard model predicts should be present at those epochs. That is not a rounding error. That is a different universe. Then there is the Hubble tension, which Webb did not create but definitively refused to resolve. The Hubble constant measures how fast the universe is expanding right now. 2 methods, 2 answers. The Planck satellite reading the cosmic microwave background arrives at 67.4 kilometers per second per megaparsec. A megaparsec, for reference, is roughly 3.26 million light years. Adam Rees and his SA0ES team, measuring distances through Cepheid variable stars and type 1a supernovae, arrive at 73. Many physicists assumed Webb would settle this by revealing measurement errors in the Cepheid data. In early 2024, after observing 1,000 Cepheids across 5 galaxies out to a distance of 130 million light years, the SURE-ES team published their conclusion. The measurements held, the tension did not relax. And then there is a third finding that receives less attention, but may be the most structurally troubling. Webb has observed a significant number of young galaxies with elongated stretch shapes, what researchers have informally described as cosmic cigars. Cold, dark matter simulations predict galaxies that are roughly spherical or disc-shaped in their early stages. These prolate elongated structures match predictions from alternative dark matter models, specifically warm dark matter and wave dark matter, better than they match Lambda-CDM. Cold, dark matter is not simply one ingredient in the standard model. It is the scaffolding. It determines where and how fast galaxies form, how they cluster, and how large-scale structure emerges across billions of light years. If the scaffolding behaves differently than we assumed, the implications do not stay contained. They propagate through every prediction the model makes. 3 independent lines of evidence: impossible galaxies, an unresolved expansion rate, and the wrong shapes. Webb did not find one crack. It found 3, all pointing at the same wall. Here is where the story slows down, because this is the part that cosmologists are actually losing sleep over. The standard model does not just predict that galaxies grow slowly, it predicts why they grow slowly. And that mechanism is specific, testable, and deeply embedded in the physics of star formation itself. When a cloud of gas collapses under gravity, it does not convert all of its mass into stars. It cannot. As the first stars ignite, they pour out radiation, stellar winds, and eventually supernova shockwaves that blast the surrounding gas outward, shutting down further star formation. This feedback mechanism acts as a natural brake. Under normal conditions, cosmologists estimate that somewhere between 10 and 20% of available gas in a given region actually converts into stars. The rest is expelled. That number, the star formation efficiency, is not a guess. It is derived from observations of star-forming regions across the local universe, cross-checked against simulations refined over decades. It is one of the better constrained parameters in all of astrophysics. Now take those early Webb galaxies, work backwards from their observed stellar masses. Ask the question, given the amount of gas that should have been available in those dark matter halos at that epoch, what star formation efficiency would have been required to produce this many stars this quickly? The answer in several cases approaches 100%, meaning essentially all available gas converted into stars with no feedback, no expulsion, no break. That does not just strain the model, it violates the underlying physics that the model is built on. Cosmologists are currently split into 2 broad camps. The first argues that we are looking at observational artifacts, that Webb's photometric redshift estimates for some of these galaxies may be slightly off, that what appears to be an extremely massive early galaxy might occasionally turn out to be something else under spectroscopic follow-up. This is a legitimate scientific caution, and follow-up spectroscopy has already revised some early estimates downward. The second camp is beginning to ask a more uncomfortable question. If the most extreme cases survive further scrutiny, and some already have, then we may be looking at a situation where the physics of star formation in the early universe operated under conditions so different from today that our current models simply do not capture them. Neither camp is panicking, but both are paying attention in a way that was not true before 2023. The data forced the conversation open, and open conversations in physics historically have a way of going somewhere unexpected. Let's step back from the data for a moment, because there is something about this particular crisis that is worth sitting with. Everything we have discussed so far, like the impossible galaxies, the expansion rate that refuses to converge, the shapes that do not fit, these are not abstract mathematical problems existing somewhere outside of you. They are descriptions of the structure of the reality you are physically embedded in right now. Dark energy, the mysterious force that makes up 68% of everything that exists, is not somewhere out there between distant galaxy clusters. It is here. It is in the room you are sitting in. It is in the space between the atoms in your body. Every cubic meter of the universe, including every cubic meter occupied by you, contains dark energy. We have given it a name. We have measured its effects with extraordinary precision, and we have no idea what it actually is. That is not a gap in a textbook. That is a gap in our understanding of the substance of reality itself. And dark matter, the invisible scaffolding that makes up roughly 27% of the universe, is flowing through you right now. Hundreds of thousands of dark matter particles, if the standard model is correct, are passing through your body every single second. You cannot feel them. No instrument we have built can directly detect them in that context. They interact with ordinary matter through gravity alone, and gravity at that scale is so weak it registers as nothing. Here's what that means practically. 95% of the universe is made of things we cannot see, cannot touch, and cannot fully explain. The 5% we can see, stars, planets, gas, everything you have ever encountered, is the exception, not the rule. Webb is not finding cracks in a theory. It is finding cracks in our picture of what existence is made of. And that is a different kind of problem entirely. To be fair to the science, and fairness here matters, the standard model is not going down without a fight. And it should not. Because some of the pushback against the most dramatic interpretations of Webb's data is legitimate, careful, and worth understanding. Start with the impossible galaxies. When Webb first released its early deep field images, a wave of papers appeared flagging objects with photometric redshift estimates suggesting extreme masses at extreme distances. Photometric redshifts are educated estimates. They infer distance by analysing how a galaxy's light is spread across different wavelengths, rather than measuring it directly with spectroscopy. They are useful but imperfect. And in the initial excitement, some of those estimates turned out to be wrong. A significant fraction of what were initially catalogued as impossibly massive early galaxies were subsequently identified as something else entirely. The little red dots, a nickname researchers gave to a population of compact, intensely red objects Webb detected, many of them appear to be active galactic nuclei, supermassive black holes in the process of consuming surrounding matter at extraordinary rates, so luminous that they mimic the light signature of an entire massive galaxy. Once those objects were removed from the sample, a portion of the tension with the standard model relaxed. Then there is the Hubble tension itself. Several researchers have argued that the Cepheid distance ladder used by the Shai-0ES team may still carry systematic errors that Webb has not fully eliminated. The calibration chain is long. Each step introduces a small uncertainty, and small uncertainties compound. Future data from the Gaia Space Telescope, which measures stellar distances through pure geometric parallax, may yet tighten those constraints in ways that nudge the two measurements closer together. And the standard model has survived crises before. In the 1990s, measurements suggested the universe was younger than its oldest stars. That was not a minor tension. That was a logical impossibility. And it was resolved, not by abandoning the framework, but by discovering dark energy, which changed the expansion history and restored consistency. The model absorbed the crisis and emerged stronger. But here is where the defense reaches its limit. After removing the little red dots, roughly twice as many massive early galaxies remain as the model predicts. The Hubble tension has survived Webb's sharpest instruments, and the elongated galaxy shapes persist across multiple independent observations. Einstein once called his own cosmological constant his greatest mistake. He added it to preserve a conclusion he preferred over what his equations were actually telling him. The standard model may not be making the same error, but the possibility is worth naming out loud. The good news is that we are not going to be waiting long for better answers. The next generation of instruments is either already operating or approaching readiness, and collectively, they represent the most powerful observational toolkit cosmology has ever assembled. The Euclid Space Telescope, launched by the European Space Agency in 2023, is already returning data. Its mission is to map the geometry and large-scale structure of the universe across 10 billion light years, using weak gravitational lensing and galaxy clustering to probe both dark matter distribution and dark energy behavior. It will directly test the S8 tension, the quieter discrepancy about how clumpy the universe is, with a statistical sample large enough to settle the question at high confidence. The Vera Rubin Observatory in Chile begins its legacy survey of space and time in 2025 and 2026. Over 10 years, it will image the entire southern sky every few nights, building light curves for billions of objects. Among its expected yields, thousands of strongly lensed quasars and hundreds of lensed supernovae, raw material for time delay cosmography, a method of measuring the Hubble constant that is entirely independent of Cepheids and supernovae calibration chains. NASA's Nancy Grace Roman Space Telescope, expected to launch around 2027, is specifically designed to study dark energy through wide-field surveys covering areas of sky that Webb, with its narrow, deep focus, was never built to address. Roman will observe hundreds of millions of galaxies and thousands of type 1a supernovae, providing the statistical weight needed to determine whether dark energy is truly constant or has been evolving over cosmic time. And Gaia's forthcoming data releases will provide geometric parallax measurements precise enough to recalibrate the entire Cepheid distance ladder from its foundation. By the early 2030s, the Hubble tension will almost certainly be resolved one way or another. Either the measurements converge and the crisis quietly closes, or they hold firm and the field has no remaining escape route. The universe is about to be forced to give a cleaner answer. So here is where we actually stand. 4 separate lines of evidence: the Hubble tension, the impossible galaxies, the elongated early structures, and the S8 tension are all pulling in the same direction. They are not 4 independent problems that cosmology needs to patch separately. They may be 4 symptoms of a single deeper misunderstanding. Something in the space between the Big Bang and right now, in those 14 billion years we have never directly observed in full, is behaving in a way our best framework does not predict. That is either deeply unsettling or extraordinarily exciting, possibly both simultaneously. Consider what happened in 1998. Cosmology was facing a different but equally uncomfortable contradiction. Measurements of the universe's age suggested it was younger than the oldest stars inside it. Stars cannot be older than the universe they live in. The logic was airtight. The crisis was real, and the resolution, the discovery that the expansion of the universe was not slowing down, but accelerating, driven by something we named dark energy, did not just fix the numbers. It fundamentally expanded what we understood reality to contain. The crisis was not a failure of science. It was science operating exactly as it should, pressing against the boundary of the known until the boundary gave way and revealed something larger on the other side. We may be standing at an equivalent boundary right now, not at the end of cosmology, but at the edge of the version of it we have been living inside. And here is the part worth sitting with personally. You are not an outside observer of this moment. The atoms in your body were forged in the cores of stars that lived and died before our solar system existed. The dark energy threading through the space inside your chest is the same force pulling galaxy clusters apart at the edges of the observable universe. You are not watching the universe from a distance. You're a temporary conscious arrangement of the universe looking back at itself, trying to understand its own rules and discovering that those rules are stranger than expected. That is not a reason for anxiety. That is the most remarkable situation any collection of atoms has ever found itself in. The standard model is not dead, but it is no longer unquestioned. Webb handed us the questions. Roman, Euclid, Rubin, and Gaia are being built to pursue the answers. And whatever those answers turn out to be, they will almost certainly be stranger and more beautiful than the picture we are currently trying to defend. The universe has never once turned out to be smaller than we imagined. There is no particular reason to think this time will be different.